Welcome to Forecasting Impact, a podcast brought to you by the International Institute of Forecasters. This show brings together experts from academia and industry to discuss a wide range of subjects on forecasting science and practice in business, society, economy, healthcare, and education. Thank you for choosing to spend some time with us today.
Hi, everyone, and welcome to another episode of the Forecasting Impact podcast, a monthly podcast that aims to disseminate the science and practice of forecasting, including, of course, all the latest development in AI and its applications in business and elsewhere. I'm George Boretos. I'm founder of an AI-based price optimization company, FutureUp, and I'm your host for today. And today it's a great honor to have together with us Dr. Theodore Modis. Theodore, welcome.
Thank you. Thank you for the invitation.
Well, Theodore is a highly acclaimed and acknowledged forecaster with decades of experience in the field, both scientifically but also as a business consultant and a practitioner. He has written over 100 articles, scientific and business, about forecasting, and also 10 books, both scientific and also other books, because Theodore has many different interests, but the scientific books are about forecasting. And I have a very small confession to make that I'm a big admirer of Theodore's work because he was a source of inspiration when I started my career 30 years ago, and he helped me draft my first path and my first steps into forecasting by reading his first book. I believe it's your first book, Predictions, which was a great, amazing book full of insights about forecasting and really helped me understand what is happening there, both at the scientific, statistical, but also the business layer. So thanks for that, Theodore. So let's start and talk about your career, because this is the interesting thing and this is what the audience is expecting to hear today. And let's start with the beginning of your career, because it wasn't in forecasting. It was in CERN, if I'm not mistaken, with particles experiments. So,
experimental physicist.
Yeah, so how did it happen that you moved from this, which is also amazing, into forecasting? Tell us a bit about this transition.
After 11 years at CERN, even some of them I was at the University of Geneva, I was still doing experiments at CERN. I started becoming disenchanted with the way physics was done. The experiments were becoming bigger and bigger, the collaborators more and more. At the time, we were publishing articles with 10, 20 names on them. Today, they're publishing with hundreds or even close to 1,000 names on them. And there was a general atmosphere that my work was being lost, not seeing any of my of what I'm doing. I wasn't getting feedback on what my particular contribution was in such a big experiment. And then at the same time, it happened that Digital Equipment Corporation was growing very fast, challenging IBM on the market. And several physicists of CERN had already gone there. In fact, there was one particular guy who left 10 years before me and started the management science group in Digital. And when I talked to him, he said, "Why don't you come and join us? And we're doing physics here if you want, in a different way." So when I did talk to him in more detail, I was fascinated by the dynamism, the dynamic operations of this small company. For example, in the University of Geneva, when I wanted to travel, I had to apply 2 weeks ahead of time with formulations, with paperwork and approvals and so on. Here, I talked to Giovanni Maderni, was this physicist, an Italian, who was my boss now in Digital. We had lunch together, and I said, "Giovanni, the papers you gave me to read are fascinating. This guy in Vienna does great work." I was referring to Marchetti, the physicist who was doing all these interesting papers that Giovanni gave me to read. So Giovanni says, go see him. I say, okay, whenever you want, he says. So I go back after lunch to my office, and I talk to the secretary and say, oh, I call Marchetti and I said, I'd like to come and see you. Yeah, he says, but you have to hurry because after tomorrow I leave for Tokyo. So if you come tomorrow morning, we'll have all the day between us. And it was already afternoon. I say, yeah, I will see if there is a plane. I know the schedule, Marchetti says. There is one at 7 o'clock. If you can make it, by 9:30, we'll be talking together. So I go back to the secretary and I say, can we possibly find me tickets for tomorrow morning at 7 o'clock for Vienna? And half an hour later, I had the tickets on my desk. And the next day, I was in Vienna. It was fascinating, a really big difference from the way it was done at the university and in the strictly physics environment. Anyway, so that's how I ended up in the management science group. And there, I had an open charter of do whatever you want, as long as it can be of benefit to the company. So I started looking at the work of Marchetti, which was around applying natural laws in order to predict the future. I was so excited, and I found the stuff so interesting. And I was doing physics in the pure sense. That is, I was applying physics laws in a different environment, which was much more dynamic and much more gratifying.
So yeah, I was inspired by you, and you were inspired by Marchetti. This is what I understand.
Well,
to kickstart to some extent.
By Volterra, Lotka, and so on.
Exactly. I heard about all these guys, Marchetti, Volterra, Lotka, from your work, and then I've read their articles and seen their work, and I was very, very excited to see all the applications in business. And to be honest, what excited me all of the time is that it didn't all start, I'm talking about S-curves, the competition systems and all these things, it didn't start from business. It starts from population ecology, if I'm not mistaken.
Natural growth, which gives the S-curves, the way populations grow, a pair of rabbits on a fenced-off grass field. But then competition more general, natural growth always is under conditions of competition, because there's a limited resource and there's competition for it. But then we have competition between more than one species, which is described by Volterra and Lotka. And we have the predator-prey or the parasite, different functions, different ways of interacting between two species. Then you have homeostasis, which Marchetti calls invariance. This usually happens at the top of the S-curve when there's a stabilization around a level which is optimum. Then there's the life cycles of products and whatever, which is the derivative of the S-curve, the rate of growth of this natural law. There's chaos, which happens in the beginning and the end of that growth process, when the big fluctuations in the beginning and big fluctuations at the end. Substitutions, there's a lot of substitutions, particularly in the industry, technological substitutions, cars replacing horses, or anything, electric vehicles replacing ICEs.
If we go back in time, because you have been doing that for many, many decades, I think you started somewhere in the 80s, if I'm not mistaken.
Right.
Can you remember, do you remember any of the first forecasts that you did, and if one stood out and it was more interesting? I think you can remember something.
No, I used to make presentations to the digital people who were making computers by talking about how rabbits populate a fenced-off grass field under conditions of competition, and their population, the size by 2, the 2 become 4, exponential growth in the beginning, and at the end, to the extent that they arrive at the capacity of the field to feed the number of rabbits, they reach a ceiling. and that's the curve I presented. They tell me, I invariably had an objection like, we are making computers here. What do rabbits and computers have in common? There was the joke I put together, and I answer by they can multiply. And then I specified that they can do it in exactly the same way, because we just showed them how rabbits multiply. And here's how computers multiply. That's the famous VAX 11750, a microcomputer, a mini computer. These were minis, very successful product for digital that at that time was in its highest sales rate. And here's the cumulative sales that follow nicely an S-curve. And here are the quarterly sales. So I told them that based on this historical data, the continuation of the S-curve indicates that we are approaching a ceiling and that the sales will go down from now onwards, which they didn't like at all. They told me that I didn't know business. I was a physicist. They said this little dip here is the first quarter that is always low because of seasonality. And they told me they had plans to advertise to the midlife kicker and a whole lot of things that for which they were making to extend the lifetime of this product considerably. But it turns out that the red line here came in very good agreement with the forecast. Changed a little bit at the very end, but by and large, there was a very successful forecast, and that was the first one, which established me in digital anyway as a reliable forecaster.
Is it difficult, like in this case that you just described, is it difficult to pursue business people to follow forecast or to believe forecast in real life?
It is, and only to the extent that you have success, they start to accept you and as a reliable interlocutor. In the beginning, if you tell them anything they don't like, is just because you are not one of them. You're a scientist, you're a physicist, you don't know about business, and as long as what I'm telling them they don't like. But when it comes with a successful forecast like that one, I remember the big boss of digital, he was presenting the results of the quarter in a big meeting, and he turned to me, "You were right, Theodore," he said. And that gave me credit and satisfaction.
Yeah, nobody wants to face the ugly truth. This is
exactly
a common secret among the business cycles. Regarding your books now, let's talk about your books, and not about predictions, although I love it, but I also love I think it's your second one, Conquering Uncertainty, especially the concept that you introduced there of the seasons in business cycles in business. I think that was extremely important. So can you tell us a bit more about that, its underlying rationale, and also if you can share a few examples?
I was inspired by the life cycle of products, the way marketers talk about it. They talk about introduction, the growth, the maturity, and the phasing out of the product and the end. So I say this is like the derivative of the S-curve, is the rate of growth of an S-curve. So when it goes at maximum rate, we are in the summer season. The seasons came naturally because summer is when the living is easy and the profits are high. Winter is when you have difficulties. In the beginning, at the end, the chaotic part, as we say, there's chaotic fluctuations in the early phases and the late phases of the S-curve. And then in between is a progressive growing part, which is like spring, and a progressive declining part in the fall. And so from there, I was inspired to use this metaphor. And then I assigned attributes. Now, if you want to talk about pricing, which you are interested in, pricing in summer is vendor-driven because vendors can impose their price. In the winter is customer-driven, and it may even have to be at cost sometimes because life is difficult in the winter for the company. And in spring is value-based, based as the sales grow. And in the fall, when the difficulties begin to set in, it's cost-based. So these are natural attributes concerning pricing, concerning the product, other things like in the summer you integrate vertically, in the winter you promote the new product that's going to be replaced the old one, and you invest in capacity in spring, and you disinvest, you launch the follow-up in fall. Finance, you reap the profits in the summer, you invest in with low inflation in spring, we go liquid with high inflation in the fall, and you explore, trial and error, taking risks in the winter. Now, I push this a little farther, always from the mathematical point of view. The S-curve has its equation. The rate of growth, the derivative is the bell-shaped curve, the rate of growth, and those two make a lot of sense. And the peak is at the center. The center of the S-curve is the maximum rate of growth. And then the second derivative, that's the derivative of the bell shape, it goes up and down and up, is this blue curve. And these are the prospects of growth. And this is something that we are very sensitive to our gut feeling. I mean, you can try to say where I'm on the S-curve, or you can try to more carefully or more delicately to see, is the rate of growth really correspond to where I think I am on the S-curve? But on the prospects of growth is how do you feel, optimistic or pessimistic? So you can, I have a set of questionnaire that exploits how people feel on a gut level in order to deduce where you are on the S-curve. That's the question. Where are you on the S-curve, and what to do about it, as it says on the cover of the book.
Let's talk about one of your other books, The S-Shaped Trail to Wall Street, where you introduce an innovative way of predicting stock prices. And also I know that after a few years, you also introduced an iPad application to do exactly that. So can you share more about the underlying rationale and how this works, and did it work in practice?
Natural laws work if we work with physical variables. So you cannot use S-curves on pricing. Price is not a physical variable. It's not a limited resource. So what we see here is the final result, the forecast with the uncertainty around it. And this is 5 years worth of history. It's 20 quarters. And the forecast was done when you saw the video. And then 2 years later, I have the data that came in very good agreement with the forecast. Now, this is was chosen as a good example because it's well behaved. It's rare that you have 5 years history with no mutations, no violent events happening. For the forecast, for the evolution of a natural growth curve to completion, conditions must remain the same. That's the difficulty with forecasting stock prices, that the environment is very mutational. It changes with political events, with the weather, with wars, with violence, with who's the president, what does the president of the United States says or does.
One of your most provocative forecasts is about Mozart and other geniuses and their personal S-curve that's completed almost at the same time when they died. So can you tell us how you came up with something like that and what it means?
Well, the idea is that someone's productivity and creativity is not infinite. They, when they're young, they cannot produce much or cannot create much because they don't know enough. There has to be teaching, learning, and when they're very old, old age is not propice to productivity and creativity. So you already see that there could be bell-shaped, rising productivity and lower productivity and creativity as the years go. And if we assume that's the case, then we can study people like well-documented uh, creators of art, of music, of science, or whatever. The cover of Mozart that I show you here is the cumulative compositions according to Keschel, who did the very careful classification of Mozart's works. And so he added some value by eliminating non-valid works. So if you make if you fit an S-curve to the cumulative number of compositions that have a Keschel number, you see an S-curve that is practically complete. The argument is that when Mozart died, he had pretty much said whatever he had to say. I have Einstein's curve. I want to show that too, because again here, Einstein's publications, by and large, follow an S-curve quite closely, with, again, two deviations in the beginning and at the end. In the end, we see that from a certain point onwards, the curve doesn't follow the S-curve, but goes in a straight line, like a machine that produces at a fixed rate publications. And when you look at the content of those late publications, you see that there is very little innovation, very little new material in it. Most of them are translations, publications in a popular magazines, or publications of talks that Einstein gave, because nobody would refuse a publication that has Einstein's name on it by now. So, but the content of new material is very poor.
So he tried to escape the inevitable, but actually he couldn't. By repeating himself
he
and
did, but it
himself.
doesn't count. In terms of S-curve, he doesn't count. On the other hand, in the beginning, it's interesting that the 1%, the nominal beginning of the S-curve, is when Einstein was 15, because he really wasn't a very good student. But by the age of 15, he had devoured all the writings of the great physicists, from the classic ones to his contemporary ones. So it's not surprising that by 15 by the age of 15 to the age of 21, when his first publication came out, he was already thinking of material that was worth publishing, but never made it. So,
sorry to interrupt, but I think this makes sense, because what we see here is whatever is documented, not in their minds. And obviously these geniuses think before they publish, so they have done some creative work before, and this cannot be represented here, but it is predicted and estimated from the S-curve. Possibly,
yeah, the S-curve can point out quantitatively to how much of this could there be between 1% and between age 15 and age 21. What's interesting is that there can be variants. Like here we saw, a continuation in a straight line, which is not very meaningful, but there can be a niche within a niche. Like here we have Hitchcock's film movies. The full-length features followed an S-curve rather completely, except for the very beginning, where Hitchcock had a hard time to get himself established as a movie director. When he was young, in fact, in the beginning, he was interested in theater more than in movies. But the time he started making movies, he accelerated. He made quite a few in the beginning, and then he got on this nice S-curve, which hit a ceiling well before his death. But then Hitchcock discovered TV, and he was invited to make TV movies, and he made a series called Hitchcock Presents, short TV
I've seen
movie.
it.
And these are the white points that they follow a smaller S-curve on top of the other one. You see here, these white points are the sum of TV and full movies. And that also reaches the ceiling when that adventure ends. And what's interesting here is I'm pointing out a little fluctuation that would have gone completely unnoticed had it not been in the extrapolation of the TV movies. That is, full-length features came into a crisis around the beginning of the 50s, and then television came in strong, and it cut into full-length features, so that slowdown in movies is just the beginning of the TV curve.
In business, we call this related diversification. And this is what he did, and lots of people do that, especially in the entertainment business. And now that TV is quite powerful, you can see actors, directors moving into the TV sector. You have made multiple forecasts, amazing forecasts with great implications for business or elsewhere, but admittedly your most controversial forecast is that about the complexity and entropy and practically the future of our universe. And I really don't understand how you even came up with something like that. Where do you find the data and the rationale behind this forecast? And also, what are the practical implications, if there are any, for us living today?
Right. Well, I'm not going to go through this whole slide. It's my involvement with complexity from the very beginning in 1999, when I visited my colleague and old friend, Eric Schwartz, who was a professor of cognitive and neural systems in the Boston University. And over drinks in the evening, I told him that it's moving too fast. The technology is moving too fast. And he says, oh, let me show you. I have put down some data. I want to see what kind of curve they follow. Is it exponential? Is it? And immediately I said, Eric, this must be a logistic, an S-curve. It cannot be exponential. Nothing is purely exponential. Everything at the end turns into an S-curve. But then, inspired by that evening discussion, we agreed with him that his data were very subjective, and that if you want to go publish something, it must be as possible, more as possible, as objective as possible. So I started searching for data, and went to libraries and museums and wherever you want. And I even wrote to Nobel laureates that were still alive, asking them for inputs. So I collected milestones, turning points in the evolution of humans, evolution of the world. It started by the whole world. My friend Eric said, I start with the Big Bang and I end up with internet. AI wasn't there yet. So he had 28 points like this. And my first attempt was for the whole universe. But my most recent article, which just got published in the Complexity Journal, focuses only on the human system. It's much more defensible, much more coherent, because it starts with the evolution of the of humans, from the domestication of fire, and it finishes with artificial intelligence. These are milestones. These are breaks in historical perspective. These are turning points in the evolution of humans. There are only 14 of them. And I decided that it has to be a bell-shaped curve, because complexity, many physicists have talked about it, complexity cannot grow indefinitely. If you take the famous coffee and cream example, when you first put cream on top of coffee, it's easy to describe. It has low complexity, and it has low disorder, low entropy, if entropy is a measure of disorder. When you start mixing, it becomes more difficult to describe, that the complexity is higher, and then the disorder is higher, because things get mixed up and it's disorderly. At the end, when it's fully mixed, you have maximum disorder. Everything is everywhere. Every particle of cream, every particle of coffee is everywhere. So we have maximum entropy, but it is easy again to describe, because it's trivial. Complexity is low again. So while entropy keeps growing, according to the second law of thermodynamics, complexity must increase in an isolated system. Entropy must increase. Complexity goes up and down. First grows and then declines. Another argument is the dice. You throw a dice very many times, so that it gets used up and then it becomes rounded. The edges become rounded. So here I published this article just because it's easy to calculate quantitatively entropy and complexity in absolute numbers. Information theory gives formulas of how to calculate the entropy for a dice and the complexity for a dice. And as time goes on and the dice deforms, there is a seventh possibility, not only the 6 sides of the dice, but the seventh possibility comes in, which is that of landing on a rounded corner. The more rounded the corners, the more frequently it will land on them. When it becomes a perfect sphere, it will always land on the same way. So the complexity of the dice in the beginning is what it is, 6 sides possible. Then it increases because a seventh possibility comes in, so it becomes more complex to describe. And then as the seventh possibility dominates and the others come out of sight at the end, when it becomes a sphere, the complexity becomes very simple again, practically minimum. So that is the reason I used a bell-shaped curve to describe the evolution of the complexity of the 14 milestones, which I'm listing here, which are related to humans, from domestication of fire 700,000 years ago to artificial intelligence. That was years before 2000. So I have a minus sign for artificial intelligence because it came after the year 2000. But you see, the recent ones, with the crowd together, is internet, human genome sequence, DNA, transistor, nuclear energy, a whole bunch of them together at the turn of the 20th century, modern physics, automobile, aeroplane, etc. So the gray line is what I fit the complexity of those 14 milestones, arbitrary units here, and logarithmic scale below to show how it's valid all the way back to the first milestone, because here they're so small you cannot even see them on a linear graph. So you see that AI comes to after the peak of this complexity curve. In fact, AI here is estimated to have a little more complexity than internet did, which was a lot more than nuclear energy, transistor DNA, and so on. So the next milestone is expected in about 2050, 2052, and will bring less complexity than internet, but more than nuclear energy, transistor, DNA, and so on. And that is likely to be a group of discoveries.
If I understand correctly, we're at the peak point of our evolution, at least the recent evolution process right now.
Not the complexity of the human system. Contrary to what the singularity people are advertising, this says that in the future, things will become simpler rather than more complicated.
That means less creative. So we'll see less innovation, or not necessarily.
Well, if innovation is equated to complexity, or at least if they're related one-to-one, yes, there will be less.
Let me rephrase it. If AI is successful in automating everything, so our lives become simpler because simply we have something which is called AI and automates all aspects of our lives, or most aspects of our lives. But that doesn't mean that there is no innovation. It just means that AI as an innovation is powerful enough to automate and simplify things.
AI will certainly contribute to this. But what I'm saying on this paper I just published is that humanity evolved and thrived when complexity was increasing. So if complexity is decreasing, we don't know how humans will accept and behave during that time. In fact, I'm arguing that humanity has an interest in flattening this curve, because if you flatten the curve, you will end up with more cumulative complexity over time. And that's how there's another study we did where everybody was talking about flattening the COVID curve. We published an article saying that flattening the COVID curve temporarily decreased the number of victims, but on the long run, it ended up with more victims than if we had not flattened the curve. So similarly here, if we flatten the curve, we'll end up with more complexity for longer, which is something that humans have demonstrated they need. The growth of the world population has followed an S-curve over, in fact, has been documented meticulously over the 20th and 21st century. It follows an S-curve that went over a maximum in 1997 and has been slowing down, aiming at a ceiling of around 9.5 billion people by mid 21st century. So, but what's interesting is that the rate of growth of the world population went over a maximum in 1997, which corresponds to right here before AI, right after the internet, and then it's a bell. The world population, the rate of growth of world population follows a bell-shaped curve that precedes the complexity curve by 25 years or so, which is about the time a newborn needs before he can add complexity in a significant way to the environment. So the
important thing is that we still need people for
we
that.
still need people. In fact, the fact that people are going down, the fact that the population of the people is going down, the rate of growth is going down, has as a consequence the complexity going down. That's what I'm arriving at.
So we need diversity. Lots of people getting born in different countries, civilizations, whatever, cultures.
You cannot fit many more people on Earth. So the rate of growth of people will go down, and the rate of complexity will also go down. This points here. This is 2050, but this is more like a few hundred years later, and they spread out. Here they seem close, but in time they spread out quite a bit. So complexity will go down one way or another.
This is very interesting. And I was thinking of what you said before, sometime that S-curves cascade many times. So is this the case now as well? So we're seeing the exhaustion and mature of the first growth phase of the complexity, and there will be another one coming up the following years, decades, centuries, or not?
Well, if there's going to be another one, it's not going to be by humans, because you see this complexity curve, the S curve that corresponds to this, begins with domestication of fire, and it is halfway completed here. So by the time it ends, I think we're talking about the end of the human system. Certainly, if the beginning of it is the formation of our solar system, and the end of it's the end of the solar system, then again it's an S curve that was halfway completed. No, this S curves cannot have continuations unless, as I say, we are not talking about the human species anymore. Something that will replace humans. I don't know what that can be, but
AI.
AI.
This is what everybody thinks.
Conceivably.
Let's go back to more earthly matters, and let's talk about an important emerging market, that of the electric vehicles, the EV market. It's the talk of the town because of Tesla, possibly, and because of Elon Musk, because of the Chinese now entering the market very aggressively the past few years. And Theodore, I understand that you have published a forecast and an article about the market. So can you share a bit more about that and the prospects that you see?
Yeah, what motivated me to write that article was the observation that electric vehicles were coming into the picture very rapidly. They were selling more and more, faster and faster. And I was suspecting, and I confirmed that later, that there isn't enough electricity around. So the big advantage of electric vehicles is that they are non-polluting. That's how they are sold. That's why that's the raison d'être plan. The reason for their existence, the main reason for their existence, is that they will help the environment. But if the electricity they burn is produced by burning fossil fuels, we're not getting anywhere. They're just as polluting as the other vehicles. And I was able to show that the growth of the number of electric vehicles on the road is much higher than the rate of growth of green electricity. Green electricity is very slow. It grows, but very slowly. So by the 2030, I think 2032, I estimated, I calculated by 2032, every electric vehicle that comes into the market will have to burn exclusively non-green electricity produced by fossil fuels. Possibly much earlier, because there are many other demands on electricity, particularly, not the least of which is AI. AI makes big demands on electricity, and cars make big amount of electricity, and there isn't enough around. So, in fact, I do want to go and look again, because that article of mine was published 2-3 years ago. With more recent data, I want to look first on the substitution electric vehicles for internal combustion vehicles. There is a substitution there, but I want to quantify that and see to what extent it proceeds and what its future is. And secondly, I want to update the green electricity production, because that seemed to go very slowly, and there is a bottleneck. We're going to end up with cars that are supposed to not be polluting, but they are polluting, and electricity demand that has to be, whom are they going to give it first? To AI, to vehicles, to houses, to refrigerator, to air conditioning. Air conditioning demands more and more electricity because the weather is getting hotter and hotter. So these are two issues that I have in my mind about exploring. And I think the electric car craze is a local phenomenon. I mean, I think they're overshooting the number of electric cars they're selling. And they will have to settle back to a more normal diffusion of this new product. Now, whether it's Chinese or American, I'm not surprised it would be Chinese, because Chinese is replacing America in practically every aspect for a number of years now.
I think that's the case as well. I mean, it's quite obvious with the new Chinese, they're not new anymore, but the Chinese manufacturers for EV, and they are not the first and leading right now all around the world, but they're substituting mostly Tesla, who is the leader in the rest of the world. So it's quite obvious that China is coming up very, very strong. But definitely the market staying.
That could be an interesting substitution. Chinese EVs for American EVs. That is probably another substitution. If I can find the data. And these substitutions always take place along S curves, because there's competition, obviously, and there is a limited resource. You can only substitute 100% of the previous one. So the conditions for S curve are there, and there's no uncertainty of the final maximum. So a few points will give you a very good forecast for this kind of substitutions.
And I think there is published data all around the web, so you can find something. And we'll be looking forward to this new forecast. If you choose to do that, it will be great. So let's talk a bit about the forecasting field and market and how it evolves, and especially which applications of forecasting in business or elsewhere you think will prevail the following years, will be the most important the following years.
Well, my point of view is always from a physicist point of view, and my experience is that forecasts are reliable if they are based on laws, because laws are invariant. They're always valid, and so the forecasts that will become successful are those that are based on natural laws, and those that have historical windows during which the conditions prevail also in the future. There's no violent changes in the conditions of the evolution of the whether it's an S curve or whether it's a cycle or whether it's an invariant or whatever we are forecasting a substitution, whether the conditions do not change in a way that have never been seen before. So as far as I'm concerned, these are the forecasts that could be successful. Now, obviously, the forecasts which are mechanical, like line fitting and linear regression and a whole lot of other typical forecasting techniques, I think they will be taken over by AI, because it can do it much better, and these are formulas well described. It's much more difficult for AI to imagine. For a while. It would be difficult to apply laws of nature to forecast stock markets or other phenomena, even though I wouldn't be surprised if at the end AI will do everything, because it evolves so rapidly that it will probably do that as well. But in my mind, the AI will come in first into the traditional forecasting techniques, and later to my forecasting techniques, which are based on natural laws.
So regarding forecasting, regardless of if you are using statistical methods, AI, or anything else, and based on your experience, how accurate can this be? And can we really base our decision making, especially in business or elsewhere, on forecasts or not?
As I said, for the forecasts that use S-curves, we have published a long time ago how to calculate the uncertainties with probabilities, depending on how much of the S-curve we have as a data, what's the uncertainty per point, and what's the confidence level we are demanding. I want a 95% confidence level. That is 9.5 times out of 10, the answer I predict will be correct. So we have given tables for this kind of forecast. And again, it is an S-curve forecast over a period of a historical period. And you have to know what is the error per data point. And you have to know how much of the range of the S-curve you are covering, and what confidence level you are demanding. And that can be quantitatively evaluated. If you have very few data points, and you try to make an S-curve on very few data points, obviously there's going to be a big error at the end. If you want anything like 80% confidence level or even less. But if you have half of the rule of thumb is, if you have half of the S-curve, roughly, and if the error per data point is not more than 10%, then you can estimate the final ceiling with an uncertainty of plus or minus 20% with 95% confidence level. So if you have half of the process, the next half is reasonably forecastable.
Now, you have a company called Growth Dynamics, is a consulting firm. So can you tell us a bit more about what you offer and how you help companies?
This is the book that I describe in detail. This is only for the people who are interested to make forecasts, and the company that would devote a little group or at least one person full-time to doing forecasts with the methodologies that I use. And this can be of help to, self-help. Now, other than that, in my company, as you say, I offer a number of tools.
What's next then for you? Do you have any new initiatives or projects in mind that you'd like to share?
As I said, I want to study these two things, the vehicles and the energy evolution. And then also I want to disseminate the complexity conclusion, which is innovative and, as you said, somewhat controversial. I'm trying to put together a popularized article, the type that you read on Scientific American or Discover or popular magazines, because I think that it could be of interest to a greater public than just the narrow science audience that read these papers.
So, if anyone wants to discuss with you any research or business project or initiative, how can they get in touch with you?
Oh, with my from the website, my contacts are there. My email is there. growth-dynamics.com. I'll be glad to talk to people.
Anything else you want to share, especially
Uh,
to younger people doing their first steps into forecasting?
Forecasting is, Marchetti has said that, and he struck me. It's the most sophisticated and the most important function of the nervous system. We do forecasting all the time. In Aristotle's concept of entelechy, entelechy is the cause of something being in the future, not in the past. This doesn't violate causality. It's just a particular kind of forecast. That is, the wings of a newborn bird develop. The way they develop is a forecast of the dynamic properties of the air. A lion that hunts, we have to forecast a whole lot of trajectory and time its muscles accordingly in order to catch its prey. Or the tennis player has to forecast where the ball will go before it hits it. Forecasting comes into our life all the time. Physicists do nothing but forecast, but they call them calculations. They don't call them forecast. Forecasting is fundamental and a good field for a young aspiring student. Also, I've teased my forecasting colleagues who indulge in alternative futures. I used to argue that the past has been one, and I guarantee to you the future will only be one. So it's best to try to forecast it as well as possible. Forecast is the key.
So, forecast is key for everything. And I think we can stay with this important insight. Thank you, Theodore, for joining us today for this episode and sharing your amazing story and important experiences and insights about forecasting. And thanks, obviously, everyone for watching or listening. I hope you enjoyed this episode and that you will be joining us in other episodes of the Forecasting Impact podcast. So thanks, everyone. And again, thank you, Theodore, so much for joining us today.
Thanks for having me, and good luck.
Thank you for taking your time and listening to Forecasting Impact. If you liked this show, please subscribe to our podcast and leave a review. We appreciate you, and we look forward to seeing you at our next episode.